Welcome. In this project, our objective is to recreate a simple zero-sum two-agent soccer game and experiment different variants of correlated Q-learning algorithms. We use burlap for modeling the game and running the experiments. We model the game setup as 2x4 grid leverage from burlap grid game example. Two circle represents the agents, the inner small circle represents the ball, and it is in position of the blue player in this picture. The figure depicts the initial state of the soccer game with two agents, two observing states, and one soccer ball in a joint state space. Agent action includes moving north, east, west, south, or stick. Agent with the ball in his goal earns him a reward of +100 and a -100 for the other agent. The terminal function is defined as when an agent scores a goal, the game will be reset. Let's move to the actual experiment and the results. All our experiments follow a typical strategy wherein two multi-queue agents are made to use a joint policy defined by the type of algorithm we run. The first is the friend queue algorithm. Key parameters are chosen as recommended in the paper. The learning rate is modeled as an exponential decay rate. The max Q solver is used for maximizing the highest Q value. Explanation epsilon is set to 0.2. The gamma is set to, discount rate is set to 0.9. The result is that there is it converged quickly in about 20,000 iterations, and the final sum of the game is 0. The graph follows the paper closely, but the Y values differ. The next one is the 4Q. Minimax joint policy was set as the learning policy for these agents. Epsilon changed to 0.1 and Q initialization changed to high default values. We were unable, however, to run for more than 20,000 iterations, so we can only see the converging trend after about 5,000 iterations leading to 20,000 iterations, but we do not have enough data to confirm the paper results. So if you look at the graph, we'll see that our results are increasing, but then slowly they start diverging. If we were able to run it for 1 million, probably would have reached or depict what exactly the paper shows, but right now we don't have that data to show. And the next is the CEQ. This was the toughest of the lot, and we were unable to get meaningful data to present to the viewer. Playing the main setbacks are the agents would play for more 200 moves, and sometimes the game would never end. Agent always defend in spite of changing the epsilon. This was described in the paper, but somehow changing epsilon or changing the discount rate did not really help. So we weren't able to successfully run this and not get any data, and hence we lack figures for this. And then finally the Q learning, which is the naive Q learning. We modeled two single agents in the same soccer world, and they do not have a joint action, and they never converged, and agents always are in search of the pure policy, which they will never find, and they never converge. And the results, if you look at the results are not quite identical. They are kind of little questionable. They seem to be converging, maybe due to the decaying parameter, but still I don't see sporadic values for Q differences, just like what the paper depicts. So this is something that I might have to recreate and reproduce, but the results somehow have the same trend, but that's what I'm presenting now. And in summary, we successfully modeled the soccer game in burlap, and it was quite straightforward. Results are consistent with the theory of two-player zero-sum Markov game. The friend queue converges at all state action pairs, and 4Q shows trend of convergence. The graphs indicate that they are converging but do not follow the paper exactly. Some of the possible reasons are finer game mechanics are omitted in the paper, and I made assumptions about the choice of policies, and for some reason sometimes I might have oversimplified certain logic, like the ball position and who needs to be in ball position. Also to mention, the canned algorithms in burlap are certainly not built for millions of iterations. That was a major setback, and I somehow